Hello friends, in this video we are going to study about bimetallic thermometers which are used for the measurement of temperature in the industries. Here we will study its construction, its principle of working, then its advantages, disadvantages and its applications. So let us start with our topic. So this word bimetallic thermometer, it is having the term bimetallic, means there are two metals and the combination of these two metals is used for the measurement of temperature. So bimetallic thermometers, they are used for the measurement of temperature in the process industries. So it is an industrial instrument which is mostly used in the case of industry, not a laboratory type of instrument. Now these thermometers, bimetallic thermometers, they uses two fundamental principles. And the working of these bimetallic thermometers, it is based on these fundamental principles. The first principle says that all metals expand or contract with the changes in temperature. So as there is any change in temperature, so the metals, they are either going to expand or contract. So it is the feature of all the metals that with the change in temperature, they are going to expand or contract. So that is the first principle. Now the second principle is that the temperature coefficient of all the metals is different. So the rate of expansion or contraction for the metals is also different and they are going to expand and contract at different rates. So first principle is that every metal is going to either expand or contract, and second principle says that they are going to expand and contract at different rates. So these are the two fundamental principles on which the working of bimetallic thermometer depends. First is all metals are going to expand and contract with the change in temperature, and second is that temperature coefficient of expansion is different for different metals, so the rate of expansion or contraction is also different. Now bimetallic thermometers, they are also made up of two metals. So when there is any change in temperature, these metals are going to either expand or contract. Now their rate of expansion and contraction is also different. So due to the difference in the rate of expansion or contraction, the bimetallic thermometer, it is going to bend or it is going to change its shape according to the expansion and contraction of the metals. And this change or this deflection is proportional to the change in the temperature. And this principle is being used by in the bimetallic thermometers for the measurement of temperature, because due to the change in temperature there is a change in the shape of the bimetallic thermometers due to the different rate of expansion and contraction of the metals, and that deflection is proportional to change in temperature. Okay, so that is the main principle, that the difference in the thermal expansion rate of the two metals is used to produce deflections, which is proportional to the temperature changes. Now comes the construction of bimetallic thermometer. The bimetallic thermometers, they consist of a bimetallic strip which is made by bonding two metals together at a temperature. So bimetallic thermometers, there will be a bimetallic strip. Okay, means this strip is constructed or made by bonding together two thin strips of two different metals. So suppose that this is the one strip of metal A and this is another strip of metal B. So both these strips are combined and a bimetallic strip of these two metals is made, and this is the bimetallic thermometer. Now when this bimetallic strip, it is subjected to any change in the temperature, means first it is kept at temperature T1, after that it is kept at temperature T2. So these are two different metals, so their rate of expansion or contraction will be different because they will be having different thermal expansion coefficient. So both these metals are going to expand and contract at different rates. And due to this difference in the thermal expansion rate, there will be a bending of this bimetallic strip. And this bending or this deflection of the bimetallic strip is proportional to the change in the temperature. So when same change in temperature is applied to both these metallic strips, so they are going to expand at different rate. Okay, and these metallic strips change their length at different rates, due to which bending of the metallic strip occurs. So the bending is proportional to the change in temperature, and this is how the temperature can be measured by the bimetallic thermometers. Now let's see the diagram for the bimetallic thermometer, that how it look like. As I've said that it consists of two bimetallic strips. So this is the bimetallic strip. It is fixed at one end and the other end is free. Now when this bimetallic thermometer, it is subjected to any change in temperature, so the metals are going to expand or contract at different rates, due to which bending of this bimetallic strip will occur. So by measuring this deflection from this straight position, we can find out the change in temperature. Okay. Now, as I have said that this deflection is proportional to the change in temperature. So, if we draw the characteristics between the deflection and the temperature changes, there will be a linear characteristics. Okay, so this deflection is proportional to the change in the temperature. Now, the range over which this linear relationship between the temperature and the deflection it exists, it depends upon the combination of metals which are used for the construction of the bimetallic strip. Now, let us derive the relationship between this deflection and the change in temperature. So, this deflection, it is directly proportional to the temperature change and also square of the length of the strip. Okay, so deflection is directly proportional to the temperature change and square of the length of the strip, but it is inversely proportional to the thickness throughout which the linear relationship or linear portion of the deflection temperature characteristics. So the thickness of this linear portion of this characteristics, the deflection is inversely proportional to it. So by using this, we can get the formula for the deflection. Now, as I have said that when this bimetallic strip, it is subjected to any change in the temperature. Suppose that earlier the temperature is T1, after that temperature is T2. So, temperature difference is T2 minus T1. Okay. Now, when this temperature change is being occurring, so the bimetallic strip, it is going to bend and take a form of a circular arc. Earlier it was in straight. Okay, straight strip was there. When temperature changes are occurring, it is going to bend. Now it is in the form of a circular arc, and this circular arc will have a radius which is given by small r. Now this radius r can be calculated or is given by the relationship small t So the radius of the circular arc, uniform circular arc is there. It is given by T 3 1 plus m whole square plus 1 plus mn multiplied with m square plus 1 by mn divided by 6 alpha a minus alpha b T2 minus T1 1 plus m square. Okay. Now this T is the total thickness of strip. Total thickness means that if this is the strip, then this is the total thickness. Okay. After that, we are having N and M. These are the constant. M is the ratio of thickness. Ratio of thickness means that suppose this strip is of metal A and this strip is of metal B. So total thickness is T, but thickness of metal A strip is TA and thickness of metal B strip is TB. Okay, so T is equals to TA plus TB and its ratio is M, that is TB by TA. So M is ratio of thickness. After that N is the ratio of moduli of elasticity. So suppose metal B is having modulus of elasticity as EB and metal A is having modulus of elasticity as EA. So it is EB by EA. Okay. After that we are having alpha A, alpha B. These are the temperature coefficient of expansions for metal A and metal B. Temperature, or we can say thermal expansion coefficients. Then T2 minus T1. T2 minus T1 is the change in the temperature. So in this way we can measure the deflection in this bimetallic strip or bending in the bimetallic strip caused due to the change in the temperature. Now, if we see that in what direction this bimetallic strip is going to bend, how the direction is being decided, then the bimetallic strip, it bend towards the side of the metal which is having lower thermal expansion coefficient. So this bimetallic strip is going to bend towards the side of the metal which is having lower thermal expansion coefficient. So suppose that this is metal A and metal B. Metal A is having greater thermal expansion coefficient than metal B. Now, first we were having temperature T1, after that there is temperature T2. Now, if temperature T2 is greater than temperature T1, means there is an increase in temperature. So, it is going to bend towards the side of the metal which is having lower thermal expansion coefficient. So, metal B is having lower thermal expansion coefficient. So, strip is going to bend like this. Now, if there is a decrease in temperature, means if T2 is less than T1, then this strip is going to bend towards the side of the metal which is having greater thermal expansion coefficient, vice versa. So, it is going to bend like this in the side of metal A. Here it is bended in the side of metal B, and in the second case it is bended in the side of the metal A. So this is how the bending of the bimetallic strip occurs according to the value of the thermal expansion coefficient of the two metals A and B. Now this was the case when the bimetallic strip, it is in the form of a straight strip, and it is bended in the form of a circular arc. Now let us consider the second case in which the strip is in the form of a cantilever beam. So when the bimetallic strip is in the form of a cantilever of length A, again the strip is going to get a circular shape when there is a change in temperature. Let's see the diagram for this. Now if we consider the earlier case where we find out the radius of the circular arc here. Now in this case, if we take the ratio of the thickness, means if we take the thickness of these two metals as equal, and if we also take its moduli of elasticity as equal, then these two ratios m and n will be 1. Okay, means if ratio of thickness, the thicknesses of metal A and metal B strips is equal, also their moduli of elasticity is equal, then this formula is reduced to R equals to 2T upon 3, because here we are having 3, this is 1 plus 1, 1 plus 1, 1 plus 1. Okay, so we are getting here 2T upon 3 alpha A minus alpha B and T2 minus T1. So that is the special case when we have taken TA and TB as equal and EA and EB as equal. Now if in the cantilever type of this strip, when the strip is in the form of a cantilever of length A, length L, so here total length is L and the thicknesses is again equal. That is, metal A is of thickness T by 2, metal B is also of thickness T by 2, and the total thickness of the metallic strip is T. Okay, now when this is subjected to any change in temperature, it is going to bend and a pointer is being attached here. Okay, so when this bimetallic strip is going to bend, this pointer is also going to move over the scale, and this movement of this bimetallic strip will be measured with the help, or it can be read with the help of the scale. So directly we are getting the changes in the temperature, or we are getting the measurements of the displacement. So here each strip is of thickness T by 2. L is the total length of this strip, and when the changes in temperature occurs, it is bending. Okay, so if this is the radius from this position to the center of these strips, so R plus this thickness is T by 2, so this total is R plus T by 2, and this is R, and this deflection angle is theta. Okay, now if a pointer is attached here, so when this is going to bend, this displacement can be measured on the scale. So if we write an expression for this type of strip, so R plus T by 2 upon R. Okay, means R plus T by 2 is the expanded length of this strip of metal A, and this R is the expanded length of the metal strip of the metal B. Okay, so this is for metal A, and this is the expanded length of strip B. Okay, now let's write the formula for this. Expanded length of strip A means the total length multiplied with 1 plus alpha A, that is the thermal expansion coefficient of metal A, multiplied with the temperature difference. Okay, and the expanded length of strip B, again the total length 1 plus alpha B and the temperature difference. Now from here, if we derive the value for the R, then R is equals to T by 2, because L and L will be cancelled. Okay, and here we are having R plus T by 2 upon R. So if we take R common and then if we solve this, so T by 2, 1 plus alpha B, T2 minus T1 upon alpha A minus alpha B, T2 minus T1. That will be the value or the expression for the radius of the arc. Now in this equation, if we suppose that one of the metal is having very small thermal expansion of coefficient, suppose like metal B is having the smallest, so let it be equals to 0. So if it is 0, then this term can be neglected and R is equal to T upon 2 alpha A minus alpha B, T2, sorry, alpha B is 0, so it is not present, T2 minus T1. So R is equals to T upon 2 alpha A, T2 minus T1. So you can see that if we see this relationship, it means that the deflection is directly proportional to the change in the temperature. Now in this bimetallic strip, one end is fixed and one end is free. So deflection of the free end is proportional to the change in the temperature, and if we are connecting a pointer with this free end, then the movement of the pointer or displacement of the pointer on a scale can be used to measure the changes in the temperature. Now in that diagram, we have seen here that a pointer is displaced over a scale, or a pointer is moving over the scale. Now if we connect this movement to a secondary transducer which is converting the displacement into an electrical signal, so we can use this for the generation of an electrical signal also. So secondary transducer is going to convert the displacement into an electrical signal. Like we can use the potentiometer. In the potentiometer, displacement is converted into a voltage. So electrical signal is generated, and primary transducer will be, or primary device will be, the bimetallic thermometer. Because bimetallic thermometer it is converting the temperature or changes in the temperature into the displacement. Okay. Now this bimetallic strip which we have studied here, which is in the form of a strip which is of length L, this is unsuitable for use in some conditions. In industrial applications, it cannot be used because the deflection which is caused, that is very small. So that small deflection cannot be used for the industrial application. Deflection is small and so sensitivity is low. So to increase the deflection and to increase the sensitivity, the length of the bimetallic strip is increased. And how this length can be increased? By shaping the bimetallic strip into either a helix or in the form of a spiral. So these types of bimetallic strips which are in the shape of a helix or a spiral, they can be used in the industrial applications because in them the length of the strip is being increased. Let's see the shape of the helix and the spiral type. In spiral type, so this is the bimetallic strip which is in the form of a spiral. You can see the length is being increased. This white portion is for the metal A and this blue portion it is for the metal B. This is the free end and this is the fixed end of the tube. Okay, now to the free end pointer is being attached which is moving over the temperature scale. So the movement of this scale over of this bimetallic strip, it is directly calibrated to read the changes in the temperature. Now if we see the helical shape, so in that so in the form of helix the strip is being present and to this is the fixed end and this is the free end. So a pointer is being attached and this pointer is moving over a scale. So these spiral and helical type of bimetallic strips, they are used in the industrial applications like spiral is used in ambient and air conditioning thermostats. Whereas this helical, it is used in most of the process applications. So these are the various types of bimetallic strip. One in the form of a length, means a straight strip is there. Then the others in which the bimetallic strip is in the form of a spiral or in the form of a helix. Now comes the construction that of what material these bimetallic strips are made up of. Now, as I have said that different metals are used because we are having two metallic strips here. So different metals which are having a large difference in their thermal expansion coefficient, those metals should be chosen for the material or for the construction of the bimetallic strip. Example is nickel iron alloys. They are mostly used for the bimetallic strips because they are having a very much thermal expansion coefficient, very large value of it, so they can be easily used for it. Now, bimetallic thermometers, they are protected from the wear and tear and from the damage due to the environmental conditions by the use of the protective wells. These protective wells, they increase the response time of the bimetallic thermometers. So they not only protect but also increase their response time. Now come to the advantages and disadvantages of bimetallic thermometers. They are very simple, robust and inexpensive instruments. So they are very simple, robust and inexpensive. Accuracy ranges from plus minus 0.5% to about plus minus 2% for the industrial applications. They are recommended for use not above 400 degrees Celsius. So the temperature, if we want to measure, its temperature ranges below 400 degrees Celsius, because above 400 degrees Celsius the metals, they are going to expand at different rates, so wear and tear and damage of the material can occur. So these were the advantages. Now comes the disadvantage. So there is a temperature measurement limitation that not it cannot be used above 400 degrees Celsius, because the metals, they are subjected to some restrictions above these temperature. The metals are having some limitations for that. So its temperature range is also limited. Now, when the metals they are expanded or they contract after coming to their original, or when the temperature is being decreased, the metals they do not come to their original size and shape. So when the next measurement is being done, incorrect temperature values are measured. So every time calibration has to be done for the bimetallic thermometers, because the metals they do not return to their normal conditions. So these were the advantages and disadvantages. Now comes its applications. Now, bimetallic thermometers, they are used to measure the temperature in the process industries for the local temperature measurement. Process industries like in refineries, in oil burners, vulcanizers, hot solder tanks, hot wire heaters, tempering tanks, and impregnating tanks. So in all these conditions, the bimetallic thermometers they can be used for the measurement of the temperature. So in this video, we studied about the temperature measuring device bimetallic thermometer. Here we studied its construction, its principle, its working. Then we derived a formula for the deflection. Then we studied the types of bimetallic thermometer, then its advantages, disadvantages, and in the last we studied its applications. So I hope that this topic is now clear to you. Thank you.